Hello and welcome to another exciting episode of Beyond the Grid. I'm your host, Swaroop Karya. I realize that we haven't done one of this in a couple of months now. Just work and life gets in the way of any passion that I have to pursue. Anyways, we have a great guest today, Bryan Sachs. Bryan is a technical leader with IBM's energy and utilities practice in Canada. He was also the former global CTO for IBM's E&U practice across the globe for IBM Technology. Welcome, Bryan. Welcome to the show.
Thank you very much. Thrilled to be here.
Yeah, we have known each other for, I guess, 4 or 5 years now, but I'm so glad to finally sit down and have a meaningful conversation for about an hour in a wide range of topics. But before we get there, let's start with your personal journey a little bit. How did you start? How did you get into utilities as a space, the technology as a space, all of that? A little bit. So the audience know where you're coming from.
I guess a bit by accident and a bit on purpose. I'm not an engineer by trade. I didn't take schooling or education in order to get into the power industry. My background's in math and computer science. I started off as a techie at IBM doing work in things like internet commerce and payment systems, that type of thing. I took on a mission for mobility when it was first arriving, and at the same time, smart meters came out. And we somehow connected. And one of the first things I did was work on the ISO project for the kind of central meter data management system for Ontario. And so I did the design for that. We won the business. And then I went and did delivery on that for a couple of years. So through that, I started to pick up some industry skills. And from there, I kind of rolled off and we were starting up this Tiger team for utilities in Canada. So they asked me to be the architect on that team. I then went on to do, ADMS implementations and really start to understand the challenges that are happening within the industry. So it happened a bit by accident, but I started to pick up and really understand and learn what the industry was all about. So from there, I actually got picked up. We were doing a partnership with Apple. And I was asked to lead the energy and utility industry for the Apple partnership, building applications for field service and for other things that are, specifically targeted at what we're doing in our industry. And then from there, grew on and took more and more within asset management, built products for vegetation management, and then became the CTO for the industry. So early days was really accidental. And then from there, it became a bit of a passion and found ways to grow into the role and learn more.
Awesome. So you've seen several waves of technology coming and influencing how we do things. Starting with advanced analytics, cloud, smart grid, smart meters, now AI, and more specifically generative AI and foundation models and whatnot. Is there a specific trend that you think has been more transformative than anything else?
I think the willingness to investigate and explore new uses of technology. And what I mean by that, a lot of what we do in utilities, it is very, very defined, right? I need a customer management system. I need a control system if it's in transmission and EMS and distribution, a DMS growing into an EMS. These are kind of common functions. We rely on package solutions to do that kind of work. We try and put as much kind of control and rigor into the way that happens. And I think what I've seen kind of emerging, and I guess starting with smart meters, is the access to data that we have has just exploded. And with that opportunity. And so the question then is, how do you leverage that, both within the traditional way in which you operate the grid, but also what are some new strategies and ways that we can take advantage of that data?
So how about the flip side of it? What are the operational challenges? What I mean by that is there is a lot of growth, electrification happenings, data center growth is, nightmarish to a lot of people in terms of just management, energy costs and all of that. There is decarbonization efforts that need to happen, sort of connected to, again, electrification. Extreme weather, that's another big problem, right? What are some of the common operational challenges that's important? And how is this technology transformation feeding into all of that?
Yeah, it's interesting. I mean, a lot of it is related to the notion of climate change, right? And utilities are really interesting because they're seen as a prime contributor through a lot of what we do with fossil generation required, but a challenge. But on the flip side, billions of dollars in assets are deployed over a massive field territory that's primarily exposed to these conditions. So they are getting hit by climate scenarios they've never had to experience before, and also under pressure to change the way in which they generate power and have an impact on the environment. There's many different facets to this of the challenges and what they need to overcome. And if we let's just look at the grid operation side of the world and dealing with climate change as an example, this is a place where we're using data in ways we never did before. And a lot of that started with doing things like outage prediction. Can I use weather combined with past outages to understand the impact of an incoming storm on my grid today? And then if I have that kind of knowledge, how does it better help me plan how I'm going to operationalize and respond to it? If I look at, going even a step further, most of the outages are caused by a combination of weather and trees, right? We have massive tree trimming budgets. So the work we did in vegetation management was to say, instead of looking at, okay, I'm going to, I haven't done this one in 8 years, I'm going to go trim this section of the territory. How can I actually use technology to look across my entire service territory at once and identify the areas of the most risk? So now I could take that same budget, but have a better impact on how I use that budget to improve overall reliability. So you're starting to see AI and data help the way in which we operate to combat some of the challenges that we have on the climate side. On the
Yeah.
flip side, sorry, I'll pause there for.
No, 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 no. What I was wondering was, I've heard of cases where, one way to observe vegetation is like you fly overhead on choppers, and that's somebody's job full time. They do this every day, and then they move to different locations. And the potential for a satellite to do the same thing without having somebody to fly over and typically and really pinpoint where to trim, where to do those maintenance activities is, I think, is very powerful. I just wanted to add that. Having seen the old model very close.
Yeah. No, and you're spot on. And I think the thing is the helicopter flights are usually for transmission corridors where we have
Correct.
a
You're
wide
right.
right of way.
You're
But in the
right.
distribution grid, we don't have that flexibility.
100%. Yes. Yeah.
Yeah.
You have to
So,
go
the
drive
notion
around.
that we're doing exactly, yeah. So I mean we're doing satellite, but we're also doing new technology, something called Geiger mode LiDAR, as an example, which get,
Yeah.
much higher resolution. The whole point of it though is just different way of getting sensor information to get us better insight so we can make better decisions, right? That's where the sweet spot is.
That makes sense. That makes sense. Sorry, I interrupted you when you were going to say something.
I think we were talking about some of the challenges that they're facing. We talked about, the operational side, but if we look on the actual grid management side, it's gone from this is something that everybody talks about, but
Yeah.
it's going from something that's relatively static and easy to predict into new renewables, new load sources, electric vehicles, intermittent generation, those types of things. So a lot of the work that's happening right now is how to integrate those components safely into the grid so that we could take advantage of those capabilities without really jeopardizing reliability.
Awesome. Yeah. So is it then accurate to say that the previous operational models are not functioning anymore? They're not going to be accurate anymore. They're not going to be useful anymore.
I wouldn't go that far. I mean, utilities are very smart. Power engineers who are building a lot of the software
Yeah.
are smart.
Yeah. Yeah.
We have a lot of natural, let's say, gates or constraints within the system to protect the grid itself. And I mean, the way that I always look at it, ideally, what we want is, all of the best information that we can then model to discreetly identify what's going to happen. And then we'd love to model off that. We don't have that all the time. And so what we do is we build contingencies into the way in which we design
Yes.
and the which we operate the grid.
Yeah.
So as we get more intermittency, as we get more challenges, some of the things we do is, put more constraints or more contingency into the system to manage.
Overbuilt.
Yeah.
Overbuilt.
Yeah. So now we want to build out and be able to do more, but in the meantime, we have mechanisms to kind of protect the grid. We want to get as much out of it as we can, which is what we're trying to do with technology, do it in a safe way as we can continue to expand and reinforce the grid.
That's probably an interesting segue to GridFM. That's one topic that we wanted to talk about quite a bit, right? For the benefit of the audience, can you explain what GridFM models are and what problem are they trying to solve?
Let me start with just a little backstory about how we got to GridFM. That's
Yeah.
probably the most useful. This was, I think it was 3 years ago from now or so. A colleague of mine by the name of Hendrik Hamon, he was our lead scientist within IBM Research for climate impact. And this was right as foundation models were starting to come onto the marketplace. And what his team was doing is a lot of work in non-language foundation models. So they did, for example, in weather. How could you use foundation models in weather? And what's really interesting there is we're trying to model a physics-driven problem in a way that doesn't use physics. And what they discovered on that is we can get some very impressive accuracy, but the orders of magnitude improvement on performance is what really made it impressive. I can get relatively similar accuracy, 2 orders of magnitude more efficiently. So the way you think about that efficiency, let's say I could do, on a certain piece of hardware, I can do 10 simulations. Well, with an order of magnitude, that could be 100. With 2 orders of magnitude, that's 1,000. So now I can
That's
do
yeah.
1,000 simulations instead of 10 simulations. We also did work in geospatial where we, partnered with NASA and we were able to look at all the satellite image for the globe. We had the European Space Agency as well, I believe. And now we built a foundation model for geospatial problems. So now, for example, like we do in LLMs, I can fine tune it for a problem, say flood modeling. And so very quickly, I can now build the most effective flood models we've ever had, leveraging this base foundation from being able to train a foundation model. So we were at a customer workshop, I think it was on AI and quantum, and we started saying, well, what if we apply this to the power grid itself? Okay. Not tangential things, the actual physics of the power grid. And that's really what sparked this conversation about what eventually turned into GridFM. Couple of notes on there. When we started talking about this, like how do you go about testing this, building this, finding out if it has value? And
Yeah,
we
and
got
particularly translating something that is a physics-oriented problem into digital, right? It's not that straightforward and simple.
absolutely. And we had some experience with that in the like weather modeling as an example.
Yeah,
So we have some techniques and we have some ways that we suspected it could work. But if you think about training a foundation model, you need massive data sets that's got a lot of variety in it, right? How you're going to use that, you need a tremendous amount of expertise. How are we going to leverage that and use that? We need to worry about the regulatory constraints. We need to worry about geographically specific things that are happening in Europe versus Canada versus the US versus South America, et cetera. Right. So we had the thought of could we build something internally? Probably not on our own. Could
yeah,
we find a customer to build this with? Not likely. Right. And so what we did is we started a community and we said, what if we got the community together and start exploring this to see, is this thing viable? How do we go about building it? How do we start tackling and solving some problems in that area?
yeah, yeah, yeah.
Yeah.
Awesome.
Um,
And so, again, for the benefit of the audience, how would GridFM be? Is it fundamentally different than any of the other models that we have, large language models that we have, or is it operationally similar concept but applied to a different set of problems?
so it's a combination of the two. If you think about a large language model, what you're doing is you're taking a paragraph and then you're doing something called masking. You're putting, taking away a few of the words and you're asking the model to fill in the blanks.
Yeah,
That's all we're really doing with large language models. If we're going to do that on something physical like the power grid, we need a way to model it like a paragraph. And so what we did as a community is we came up with the notion of a graph model, right? And if you're, into math and that type of thing, a graph structure, you've got nodes and then you've got connections between the nodes. And in our case, the nodes is a bus. The connection between them is our conductors. And the values that we have at the bus level are the things that we deal with every day: voltage, phase angle, amps, frequency, et cetera, et cetera. So by building this construct of the grid in this graph model, now I can mask parts of that graph model. What happens if I
yeah.
take out a bus? What happens if I take out a value, a sensor value? Now I have the model trained by recreating what that graph model would look like. And that's essentially how, there's some of the techniques that we've used to move forward.
So then I have two follow-up questions. One is it technology enough? Like, are you finding limitations in the technology enough to achieve its full potential, everything that you needed to do? That's one. Second, are you having success with utilities to try this on real life use cases?
Yeah.
If not, what is preventing it? So maybe whatever question you want to tackle first.
Valid question. So we approach this as primary research. So in our workshops, we started off with, different folks from national labs in the US. We had academia, we have system operators, we have various utilities. And
Mm-hmm.
so through that process, we're getting all of the knowledge that we need to in order to drive this forward. And we held a session in New York. We held another one in partnership with Imperial College in London to get a broad view, not just on the North American power system, but also on the more global power system. So that's kind of our thought process that went into how do we do this. And through there, we're exploring different use cases. How could we apply this technology? Now we kicked off working groups to actually go ahead and start designing and building. And one of the partners, Hydro Quebec, is a significant contributor to the program. We started working with them and others in the community to actually start figuring out what would it take to build this. And through that journey, we connected with the Linux Foundation for Energy and turned this into a much more structured industry program. So it's not just one vendor.
Yeah.
What we got to within that program is we released two assets that are publicly available for people to download and start using. The first thing we identified was that the data that's necessary in order to train this doesn't exist. The
Excellent.
tools that are out there to generate data doesn't exist.
Yeah.
So a huge amount of work went into building tools to create the variety of data that we need with the veracity to make sure that it can be used effectively. And there's a lot of work going on in the program about using real world data to continue to improve the way in which that data source is building these models.
Yeah.
So that's a toolkit that's available that anybody has access to that can generate these massive data sets with the type of perturbations that we need to build a model. So really, really cool stuff. And then we experimented with multiple different ways of actually architecting the model build itself. And so we tried out some different technologies. The community's still building and testing new ones to
Yeah.
improve what we can do. What we found, what we started with was power flow, right? Because it's the best way to teach the foundations of what the power grid works like. And if you think about what you use that for, one of the big things is doing things like, n minus one or n minus k contingency analysis. So the results we got were really, really impressive. And so the way that we measured this, you can actually go to the gridfm.org site. You can join the conference calls. You can join the hands-on sessions that we actually have. The way we compare them is to the way they do those types of power flow things today. Most utilities will use something called an AC solver or a DC solver. Is that something
Yeah.
that you're familiar with?
Yeah. Yeah. Broadly
Right?
familiar with it. Yes.
Pretty standard, right? AC
Yeah.
takes the most compute, but it's basically ground truth. And then DC is a way to be able to do more efficient modeling. And there are some compromises to accuracy, which is fine. And what we found was that we could beat the accuracy of a DC model with 2 orders of magnitude better performance. Right?
That's pretty impressive.
When we went to look at how we use it in contingency analysis, we found that we could get to about 97% of the accuracy of an AC model, right? With 97 or 70 times more efficiency than what we can do from an AC model. And this is like early days without, spending a lot of time and training. A lot of work is going on now to continue to improve and enhance those models.
Yeah. So just want to double click on that. 97% accuracy with 70% efficiency. What does that exactly mean?
So let's say, for example, I'm doing some type of a, n minus k contingency plan. And today with compute power, I could do 100 scenarios, right? So I could test there what happens if I remove a single node 100 times.
Yeah.
Well, now I could do 70 times that with the same compute power. So I'm looking at being able to do, instead of 100, I could do, 70,000. Right?
Yeah. But the 3% loss in accuracy, is that a big deal? Do you see that as a big deal or no?
So there's a lot of different ways to look at it. The first thing is that for many organizations, for example, they might be doing DC because they don't have the accuracy on, or they don't have the compute power to do what they need to do on AC. So, there's a question of where do we get. The way that I've looked at this and the way that I've been positioning this is that this is not a replacement for what you do today, right? So what I'm doing is getting new insights that I couldn't do before. So let's say I take those 70,000 scenarios. I couldn't do that in the past. So now instead of doing n minus one, I can do n minus two, n minus three, n minus four contingency planning. Really interesting, right? Now, but what happens with the results that come out of there? What are those interesting cases? I can still run those through my traditional solvers. So I can still take those and run them through a physics-driven calculation to validate them before they make its way into the plant. So it can be a hybrid of using these together, but it's really just expanding our ability to do scenarios that we've never had thought about the ability of doing. And so that's the way that I tend to look at it. And I think we're going to see that continue to evolve as we move forward with these types of technologies.
Got you. How about my second question?
What was the question?
The question was, are you seeing widespread adoption on these models right now to fill with practical real-time use cases? If not, what do you think is preventing that adoption?
So this is, as I mentioned before, this was started as primary research. And so the where we have gotten to has proved out that this not only has legs, but there is tremendous interest from the community. So what we have is I'd say a roadmap that the community actually builds and maintains. And part of that is doing things like real world trials on data, right? So, different participants, we're trying out different models, we're trying out different fine tuning use cases, and we're starting to do the testing, in the field for validation. I don't think it's a matter of roadblocks. I think it's more a matter of the due diligence in the use of this technology and how we can introduce it in a safe way to really bring tangible value and then expand on that value as we build confidence and capabilities in this type of technology.
Got you. Are there limitations in telemetry or IT/OT segregation, the data silos, things of that sort that could impact the efficiency of the model when it's deployed?
Always. But I
Okay.
mean, that's a foundational problem
Yeah.
across anything. But again, when I look at these types of models, there's all sorts of different ways and places in which they can be used within the organization. Some of them are on the planning side. So there's a lot of work going into, can these be used for much better load forecasting or generation forecasting? And so if you do that within that part of the business, that changes your, asset investment planning. If
Yeah.
you're, a market operator, there's so many different dimensions of where you can use that. So finding the use case and making sure that you've got the data and the guardrails in place are really what the important part of. As we work towards the grid of the future, whatever we want to call it, we can start to talk about ITOT convergence and those types of things. But I don't want to think of this as I need to get everything 100% ready and then replace my models with this new thing, which is going to automate the whole grid. That's not what it is. It has applicability in many different areas, and you have to treat it differently depending on what the use case is.
So do you envision a control center where GridFM models are side by side the operators? And do you get excited by that idea? It's starting to excite me a little bit, but I'm just wondering about what your perspective is.
So it's a really good question, right? Because we have grid operators who are getting inundated with data, right?
Yeah.
And what we don't want to do is have multiple different systems that give them different information, or they have to look in different places in order to get that insight. The grid operators, they operate in real time or near real time based on real world signals that are coming in from the field, right? And then they're going to, switch settings. They're going to do, Voltvar optimization. They're going to do whatever they're going to do based on that insight. Where I see, at least the initial use is on things like contingency planning. So can I have not a grid operator doing it in real time, but the planning function using it to do contingency analysis, and then having that influence the way in which they're going to further operate the grid under certain conditions. I can see it being used in, the engineering department doing connection studies. So now instead of spending 6 years in order to get new distributed generation or new load online, I can streamline that process by the efficiencies and the simulations that I can use with this type of an approach. So you're going to have different functions, not necessarily real-time grid operators, but you're going to see it, filtering into the overall plans and strategies for how the utility is going to, move ahead and function.
Natural extension. I know we talked about the physics problem and having to model it in a digital way. A natural extension, that question is quantum.
Mhm.
How do you see quantum playing
So
in these sort of problems?
let me back up for a second, just describe how we do it in the foundation model side.
Yes,
And
please.
so when we talked about masking and then trying to guess, what you have is something called the loss function. And the loss function is trying to figure out how far am I away from the actual answer.
Yeah.
Well, what we did in this program is we have multiple loss factors. So one of them is validating that it meets all the physical constraints of the network, right? So if it's thermal or whatever it might be. So that's the way in which we inject physics into that overall training program. So really, really interesting work here. So this is something that I see happening in the short term. Now, in the long term, quantum becomes a really interesting technology for our industry. And so we have some advanced utilities who are looking at use cases. And where we are in quantum today is really trying to understand which use cases we can tackle and which are the ones that are going to have the most actual quantum advantage. Quantum advantage being I can do it better than I can do it with classical technology. And so doing things like Monte Carlo simulations for gas contracts to understand risk would be an example. And another area is looking at overall optimization. And so we're going to see new capabilities coming down the pipe with quantum. But I think for most of our utilities, I think the threat of quantum and what it has on cryptography is a bigger immediate concern as we start to develop the technology and determine how it can really transform the way in which we operate the grid.
Awesome. What about truly autonomous grid operations? Is that a reality anytime soon?
Anytime soon,
I know I'm asking all these wild questions because I just want to get some
I like them.
wild reaction from you.
We don't, as an industry, we don't move fast. And that's a good thing, right? This is critical infrastructure that impacts every single human being in every aspect of their life. And
Yes.
the cautious nature at that and that we move forward with, we have put regulatory constraints in the way of us advancing incredibly quickly. And that's probably a good thing. So if you look at, the regulator environment, the legislative environment, what we do from things like NERC and FERC and NIST standards, those are all there for a reason, right? If I'm designing a grid as an engineer, if I'm operating a grid as an engineer, I have legal responsibilities that are
Yes,
associated with that. And so if we look at going to fully autonomous, we have to truly understand where that liability resides. Who's going to sign off on using this if there's legal liabilities that are associated with it? It doesn't mean we won't get there. It doesn't mean we're going to not leverage AI and build more automation into the system, but we're not just going to be able to go there until we can tackle, those real fundamental questions.
fair enough. Good point. How about add a layer like about the importance of cybersecurity, and the reason why I say that is utilities are increasingly becoming targets of cyber attacks. Right, we had a situation not so long ago in Nova Scotia when Nova Scotia Power was attacked. I when in my conversation with a lot of the clients, they are seeing a lot of threat actors acting against them all the time. Right, is that cyber risk becomes sort of the primary constraint on innovating with these sort of models or these sort of technology capabilities?
I would say it's the opposite. And so let me describe why. Right now, if I think about our current environment, right? We talked about IT OT convergence. There's still disparity in how those environments are deployed and run. We have a mixture of IEDs in the field or controllers in the field.
Yeah,
Some of them are 20 years old or decades old. When we deploy technology in our industry, it's for a long time, right? And so all of that introduces exposures. And so if we don't do anything, we see things like Mythos came out, right? And now it within days is identifying potential threats that we haven't known
yeah,
about for 30 years. And so all of that equipment has potential exposures that we are not prepared for. I mentioned quantum as an example. The first people who are going to have access to quantum computers with sufficient capacity to actually break encryption are going to be state actors. And there's a variety of different ways that they can leverage that. And we're not prepared for that within the industry. So when I look at what we need to do in order to adopt this kind of technologies or, do grid modernization or those types of things, I start to look at a couple of factors. So one is, how do I build a platform automation into the way in which I operate? So for example, IT and OT have different needs, but how do I provision servers? How do I configure those servers? How do I monitor those servers? How do I do patch management? Right? That has to be something that is going to be happening much more frequently. Right. And so if we're not enabled to be able to have that kind of automation, to be able to rapidly impact our systems and protect it against new threats, we're in trouble. When I look at the OT environment, I look at the equipment in the field. If I can get to software defined networks, if I can get to software defined protection and control systems, things that we're
hmm
doing with like the VPAC Alliance, right? Now I start to extend that automation into the OT environment. So now as new threats come down, I can deploy, new cryptographic packages through crypto agility, right? So that I can start to protect from new threats that are coming out. New features or capabilities I can now do from a software perspective. If we don't do that, we're in the situation we are today, where the bulk of the equipment, I still need to send a technician out to do some kind of a firmware patch. And oftentimes that's just not, we're not aware of it or it's not happening at the frequency. So the whole notion of grid modernization is really putting those underpinnings in place that allow us to react to those coming threats because they're coming faster. There's going to be more and more of them, and we need to be ready to be able to deal with them.
awesome. That's a great perspective. We talked about what Anthropic put out. It's definitely helping in terms of identifying new threats. But isn't there a risk for threat actors to get the same level of access and exploit those threats before we get a chance to?
Yeah, and that is the threat. It's the identifying piece is nice, but there's new models that are out there that apparently have the same capability that can be used by nefarious actors to do just that. And so what we need to see though is the industry be able to respond with speed to those threats, and we need the internal capabilities to be able to patch our systems with speed and the consistency to do it properly. And that's why that automation piece starts to become really really important as the complexity increases.
What maybe you sit in a very nice spot where you have access to all this information, all this resources, have visibility into what utilities are doing. What are some of the forward-looking utilities doing right now? Forward-looking things that they're doing right now. You did mention Hydro-Quebec. Their name comes up quite a bit when it comes to talk about innovation, at
Yeah.
least in the Canadian context, right? And this is not the first time I've heard the name. What are some of the other utilities doing, if you know?
So it's really interesting. Our industry is driven by we're a pragmatic industry, right? We're
Yeah,
we're not out there
you
building the
have
next
to be.
yeah. And so a lot of it's driven by geography and the regulatory environment within that geography, but also what's happening from a societal perspective. So the things that we see happening in North America are very different than what we see in Europe or what we see in Japan or in other jurisdictions. And so a lot of the advanced activity around things like renewable generation have been happening in Europe because, they're much denser than we are.
Yeah.
They're much more open to adopting new technologies like renewables, EVs, etc. So the
More connected too, right?
much
And
more.
then intra-regional transition planning, all of those things help stuff.
Absolutely. Right. So because of that, they hit the challenges earlier and they've been doing what steps they can to try and mitigate those. And there's blips along the way. That's going to happen.
Yeah.
So some things that I see happening, we spoke about the adoption of AI.
Yeah.
It's not just Gen AI, right? We've been doing AI for a long time.
Yeah.
Right. So
Sure.
getting into better forecasting, outage, veg, all those types of things, those are pragmatic ways to really improve and insulate the business. So we're seeing that happen more so in jurisdictions in Europe. We're seeing changes to market structures. So in Denmark, as an example, they were looking at new rules for flexibility market to tie into building management systems and be able to use that capacity to turn down air conditioning and to be able to sell that saved energy back into the grid. So they
Yeah.
have a market structure to enable that. But now you need technology to be able to virtually meter what's happening, to be able to, at the time, put it on a blockchain so that you have transparency across that whole value chain. So really interesting approaches to dealing with market changes. We see many utilities doing what we're talking about, which is this automation layer, which is how do we get much more effective and efficient at being able to deploy new technology and be able to manage it and run it and patch it. And then we see organizations like I mentioned, Hydro-Quebec, they have such a legacy of research. They have a whole research
Yeah.
institute. And
Yeah.
what they're looking at is working on things like quantum. They're working on things like quantum safe or post quantum cryptography. They're working with us on things like GridFM and how we can push the boundaries of where we can go with this technology and fundamentally change the way in which we operate the grid. There's areas that are looking at things like grid enhancing technologies or GETs. So how do we better utilize the resources we have? Those are more popular as an area where the regulatory environment allows them to get financial benefit out of it. In a lot of jurisdictions, if we tried to go forward, we can't put a case to the regulator to justify the cost of deploying it. So we can't get regulatory relief. So you're going to see these different behaviors. There's a lot of different things that we can do, but we have to work within the system that we have
To
and
be able to do
influence
it.
that system to advance.
Yeah. Yeah. And are there parts of this transition that utilities are underestimating? Like, I know it's a pragmatic industry. You're not
Yeah.
going to move fast enough. There are always going to be some innovators like Hydro-Quebec, but broadly, are there parts of it that some of the utilities are underestimating?
Yeah, I think we have to look at, really understand utilities. There is a handful of very large utilities
Yeah.
that are under the most strain, that also have the most resources to
Yeah.
actually
Do
make
something.
changes. Then we have this long tail that drops off pretty rapidly, where I think there's something like 8,000 utilities in the world, and most of them are very small. And so a lot of them just do not have the capacity or the capability to adopt this technology until it's mandated or it's embedded within the types of systems that they're buying from the broader community. The one area that I'm really concerned about now is post quantum cryptography. Our industry is not prepared yet for it. And a lot of what we hear is, until the regulator tells me I need to do it, or until it's embedded within the systems that I'm buying, there's nothing I can do about it. But the reality is this is going to be a long-term program to fix this. We need to at least just understand what the risk level is and then start to mitigate it like we would any other risk within the business. And so there's a lot of work we're doing right now to try and build a community to understand that, put a roadmap out. We've done this in other industries previously, but to really help utilities understand what that risk is and how they can start to mitigate the most important risks in the right time frame.
Sure. Nice. Maybe just to wrap it up, last question. For you, fast forward, what does a truly intelligent utility look like?
Oof, that's a very difficult
I
question to
know.
answer. No, because when I look at the way in which we operate the grid, the same tenets that have existed for 100 years continue to exist. We need to operate a safe grid, we need to operate a reliable grid, and we need to have a cost-effective grid. And so for our utilities, the challenge that we have is how do we get the necessary data? How do we get the necessary systems in place to leverage that data to help us make better decisions? And then how do we work with the regulatory environment to allow us to actually make those changes to be able to get the most out of the systems that we have? And so if we go to full autonomous, we talked about this earlier, does that really matter? Maybe, maybe
Yeah.
not. Right? Are we
Yeah.
squeezing out an extra 2 or 3%? Maybe, maybe not. right?
Yeah. Yeah.
Maybe it becomes critical depending on what the market models are. And so I think what I really look at is we need to have this coming together, and this happens, but of changes to the market structure, changes to the regulatory environment, and then the adoption of technology to work within those regulatory constraints to meet the market needs. And those are going to evolve over time. And those market changes are going to have a big impact on what utilities are required to do in order to be able to respond to it.
Got you. Got you. Awesome. I think we've had a good discussion so far. And as you have noticed, there has been calls coming in. These people are trying to call me to get into meetings and whatnot.
Okay.
But it's been a good 40, 45 minutes discussion. I really appreciate your insights. Um, we might actually follow up with a completely different topic pretty soon here, but I like the conversation that we had today. Thanks a lot for sparing your time, Brian.
My pleasure. Thanks for having me. And yeah, I always love talking about this stuff. So anytime you want to
Yeah,
jump,
it'll be
on,
maybe we dig down a little bit more deeper into quantum.
sure.
Okay. All right.
Sounds great.
Sounds good. You have a nice day.
Thank you. Take care.
Bye.